I am Lieutenant Colonel Schmidt from the Bomber Section of the Directorate of Aerospace Safety at Norton Air Force Base, California. You are about to see and hear a most unusual story about the aircraft you fly, a story that has made aviation history. We at the Directorate of Aerospace Safety believe the factors of this incident will increase your understanding of B-52 flight characteristics and heighten your appreciation of its capabilities. The aircraft involved was a B-52H on loan to the Boeing Company. Its flight crew members were Mr. Charles Fisher, instructor pilot, Mr. Richard Curry, pilot, Mr. Leo Kors, co-pilot, and Mr. James Pittman, navigator. Here to tell you this remarkable story firsthand is one of the Boeing pilots who was at the controls, Mr. Richard Curry.
Thank you, Colonel Smith. Our mission was to conduct a flight load survey to obtain and record the structural loads encountered on a routine low-level sortie. Special instruments were installed in the cockpit to record the stresses exerted on various parts of the aircraft. An 8-hour flight was scheduled along a route running from Wichita, Kansas, southwest to the Rocky Mountains. The mission called for 10-minute runs at 280, 350, and 400 knots calibrated airspeed at 500 feet above the ground, utilizing the low-level mode of the autopilot. The initial portion of the flight progressed as planned, with only light turbulence encountered at the end of the sixth leg. However, as the aircraft turned north in the vicinity of Wagon Mound, New Mexico, and began a course parallel to the mountains, the instruments, identified here in orange, began indicating increasing turbulence and heavy gust loads on the tail section. We elected to discontinue the low-level portion of the flight, and the aircraft was climbed to 14,300 feet mean sea level, where the air was relatively smooth. We then decided to continue the mission using the next speed schedule of 350 knots. Since the terrain elevation was steadily increasing, the aircraft flight path was approximately 1,000 feet above and slightly to the right of East Spanish Peak near Aguilar, Colorado. Wind at this time indicated 62 knots west component, but no turbulence was noted. Then at 345 knots, while accelerating to 350 knots, an area of extreme turbulence was encountered. It lasted approximately 9 seconds. With this model, I will attempt to show you approximately what happened to the aircraft when it was struck by this turbulence. The turbulence came in rapid, explosive-like gusts. The airplane was pitched up and yawed to the left, followed immediately by a very rapid yaw to the right and a resultant right rolling moment. This motion was opposed with approximately 80% left wheel authority. A high-frequency vibration was felt in the rudder pedals, and rudder pedal displacement gave no response. The elevator response was also very poor. The crew was alerted to prepare to abandon the aircraft. However, we soon realized that the aircraft still had marginal control. At this time, the air brakes were raised to position 1 to improve longitudinal stability, and a fuel transfer was started to maintain a forward center of gravity. Lateral control was aided by very small asymmetric power settings, which helped maintain the aircraft in a side-slipping flight attitude. After the aircraft was brought under marginal control, we called for assistance. The first to arrive was a Boeing Bailed F-100. This is what the pilots saw. Approximately 83% of the vertical fin had been ripped away. We immediately set a course for Wichita, Kansas, and developed our flight strategy. Boeing Flight Test had already recommended that the aft main gear be lowered, as this would be a stabilizing factor in the absence of the vertical fin. Any drag after the center of gravity would tend to stabilize the aircraft. Here, the outboard air brakes are at position 4, which is also an area after the center of gravity. Here, our airspeed is about 210 knots indicated, which is about 30 knots above the minimum recommended for this weight with flaps up. Small excursions up to 220 and down to 200 knots were made. However, 210 knots was found to be most satisfactory. At this time, the altitude was approximately 12,000 feet mean sea level. The center of gravity was calculated to be about 19%, with the vertical fin missing. The weight of the vertical fin is estimated to be about 2,000 pounds. Due to the reports of unfavorable weather at Wichita, it was finally decided to divert us to Blytheville Air Force Base, Arkansas, where surface winds were more favorable. While in the Blytheville area, making preparations for landing, we were advised to extend the tip protection gears first. Then the forward trucks were lowered. A yawing oscillation occurred during forward gear extension. However, this ceased when the gear reached a down and lock indication. We reduced airspeed to 160 knots at 10,000 feet and prepared for a long, flat final approach, hoping to be able to flare and touch down at the same speed. 160 knots flaps up approach speed was selected in order to obtain optimum body angle. We had computed a no-drag chute stopping distance of 5,000 feet. Here's the aircraft on final approach. 160 knots, outboard air brakes at position 4. All engines are near idle. Crossing the threshold, still at 160 knots, the aircraft started a slight left drift, and we decided not to hold off any longer, but put it on the runway. At touchdown, all air brakes were raised to position 6. We elected to use the drag chute, but decelerated to 130 knots before deploying it. We considered the possibility of a go-around, and had it been necessary, we would have used outboard air brakes at number 6 position. This is the B-52 at Blytheville Air Force Base shortly after landing. This aircraft was flown 5 hours in this configuration from the scene of the incident over Colorado to Wichita and then to Blytheville Air Force Base, Arkansas. A portion of the aircraft's original mission was to record the gust loads found in moderate turbulence. However, the loads we encountered were much greater than had been anticipated. An analysis of the recorded information revealed gust loads of a greater magnitude than had ever previously been recorded on any large aircraft. Well, Colonel, I guess that about sums it up.
Thank you, Dick. We at the Directorate of Aerospace Safety are indeed grateful to you for bringing us this first-hand report. A review of the data collected on this flight indicates that the airframe design criteria for future heavy aircraft should be reevaluated and possibly revised for future aircraft design. An engineering change to incorporate additional strength in the B-52 empennage is well underway at Wichita. In conclusion, let us review the things which enabled this aircrew to return this aircraft to a safe landing. Excellent crew coordination to regain positive control of the aircraft. A call for chase aircraft. A call for expert technical assistance. Reduction of airspeed to 30 knots above minimum recommended, flaps up. Proper use of air brake settings with inboard air brake circuit breakers pulled. Transfer of fuel for better aircraft stability. Extension of the aft main gear only for directional stability, and judicious use of throttles for desired power settings for optimum controllability. We salute this Boeing flight test crew for a fine job of airmanship. By bringing this aircraft back, they have supplied the Air Force with invaluable data on the gust load velocities that are often imposed on large aircraft flying low-level missions. Salutes also to the other agencies and the Boeing Company for their excellent cooperation.
Originally put into service in the early 1950s, the B-52 stood as a key deterrent in the Strategic Air Command's arsenal. With its extensive range, the B-52 facilitated the global deployment of the Strategic Air Command's nuclear weapons. In contemporary times, the B-52 takes on roles such as low-level bombing and electronic warfare. While the Boeing B-52 represents the epitome of jet bomber design, its origins can be linked to a decision made by the Department of Defense a decade prior, during a period of national conflict. Throughout a significant portion of World War II, the United States prioritized the development of established technologies. This approach was aimed to facilitate the rapid production of essential wartime tools. Considerable advancements were made in piston engines during this period. The propulsion of every American aircraft engaged in intense aerial conflicts of World War II was driven by piston power plants. Even the formidable Boeing B-29, boasting superior speed, range, and payload compared to other bombers, relied on piston engine technology. While the B-29 was initially perceived as the pinnacle of aviation prowess, its technological supremacy was soon overshadowed by a new generation of aircraft. Early in the war, the United States was taken aback to discover that Germany and Britain had pioneered gas turbine jet engines, propelling fighters at speeds surpassing the legendary Superfortress. In 1944, the American Army Air Force issued a requirement for a jet bomber capable of outpacing jet fighters. Contracts were awarded for at least 5 distinct designs. However, it was the advent of nuclear fission that ultimately brought a swift and dramatic conclusion to the war. While the B-29 was utilized to transport the nuclear weapon, only one aircraft dropped one bomb, leading to the instantaneous disappearance of the city Hiroshima. The devastating capability of a single aircraft raises the possibility that extensive bomber fleets might no longer be necessary to secure victory in modern warfare. The significant human cost paid by America to establish B-29 bases in the Pacific altered the considerations for the next generation of bombers. In the early post-war era, strategic focus shifted towards the capability to deliver atomic bombs over exceptionally long distances, and the Air Force put its emphasis on long-range intercontinental aircraft, a role that Convair B-36 Peacemaker adequately filled for some time. The giant B-36 was really a Second World War design that arrived too late for combat. It required no less than 6 massive piston engines to propel it at what were average speeds. Later on, jet engines were incorporated in pods underneath the wing to augment its propulsion. By 1947, progress was evident in the jet bomber project. During that year, 5 submissions underwent testing, although they were categorized as medium bombers. Among the jets stemming from the 1944 requirement, the B-45 emerged as the first and second most successful. Its straightforward yet efficient 4-engine design was officially embraced by the United States Air Force and entered into service in a restricted quantity, primarily fulfilling reconnaissance duties. Consolidated proposed the B-46 as another 4-engine jet bomber. With its sleek lines, it stood out as one of the most aesthetically pleasing aircraft of its time, and its performance as an early jet was quite commendable. However, Consolidated's primary focus was on the B-36 production, and the medium bomber project did not receive high priority. Designed by Martin, the B-48 was a cumbersome aircraft with 6 jet engines arranged in mid-wing clusters. One notable feature was its bicycle undercarriage, positioned along the aircraft's centerline and supported by 2 outrigger wheels on each wing. Despite its innovative elements, the B-48 did not capture the interest of the Air Force, and like the B-46, the prototype was ultimately scrapped. In an effort to compete in the jet bomber program, Northrop took its existing piston engine flying wing and outfitted it with 8 turbojets. This wing design demonstrated exceptional efficiency and was notably ahead of its time. However, due to its unconventional nature, it struggled to secure government approval. Nevertheless, Northrop's mastery of flying wing technology eventually paid off 4 decades later, with the development of the B-2 stealth bomber. Today, the B-2's wing is a symbol of cutting-edge aviation design, but in 1947, the idea was considered far too revolutionary. Without doubt, the most impressive design offered to the Air Force came from Boeing. The design of the B-47 Stratojet by Boeing benefited significantly from the manufacturer's examination of German data regarding swept-wing technology. To maximize the efficiency offered by these wings, they were crafted to be extremely thin and flexible. Consequently, the 6 engines were suspended on pylons and distributed across each wing. This configuration not only facilitated engine servicing, but also provided aerodynamic advantages for the aircraft during high-speed flight. Due to the thinness of the wings, Boeing opted for the same fuselage-mounted bicycle undercarriage as seen in Martin's B-48. The Air Force adopted the B-47, leading to the production of hundreds during the early 1950s. It proved to be an exceptionally successful design, representing a classic example of having the right design at the opportune moment. Moreover, the B-47 served as an ideal testbed for Boeing to accumulate experience in producing efficient swept-wing jet bombers. One challenge with early jet engines was their relatively prolonged time to reach full power, particularly during takeoff. To counter the issue of prolonged engine power-up, Boeing implemented various iterations of detachable rocket boosters, pioneering what became known as jet-assisted takeoff, or JATO. Following Boeing's renowned piston-engine bombers, the success of the Stratojet project solidified the company's standing with the Air Force for an extended period. The experience gained from the medium bomber project positioned Boeing favorably in the subsequent quest to develop a new long-range heavy bomber, aiming to replace the aging B-36 Peacemaker, an aircraft clearly at the end of its operational life. In a bid to prolong the Peacemaker's relevance, Convair introduced an all-jet swept-wing version designated the XB-60. However, retrofitting an aircraft originally designed during the Second World War failed to impress the Air Force. As early as 1946, Boeing had received a commission to devise a successor for the Peacemaker. The company explored a myriad of concepts, ranging from exceptionally large piston-engine aircraft to those featuring proposed compound supercharged power plants and others incorporating turboprops with jet engines driving propellers. But nothing provided the dramatic increase in performance over the B-36 that the Air Force was looking for. Recognizing the remarkable efficiency of the B-47's fully swept wing, Boeing proposed another all-jet design, loosely based on its medium bomber but significantly larger in scale. This concept evolved into the Model 464-67, and it was eventually embraced by the Air Force as the B-52. An order for two prototypes, the X and Y models, was issued in October 1948. However, due to minor issues with the X model, the YB-52 was completed first. The YB-52 underwent testing at Edwards Air Force Base. While its overall shape and fighter-like canopy resembled a B-47, its size and performance far exceeded it. The B-52 featured numerous advancements, including the all-steerable undercarriage that could align forward during landing, when even the aircraft veered to one side, a top-secret feature for several years. Apart from the cockpit layout, changed to a conventional side-by-side airliner arrangement, there were minimal external differences between the prototypes and the B-52s that entered production. Work began in earnest on the B-52A, now named the Stratofortress. Initially, only 3 B-52A models were constructed, but the B model, nearly identical to the B-52A with minor improvements, entered full-scale production. Enhancing the bomber's range was a consistent priority. In-flight refueling, perfected in the late 1940s using Boeing's flying boom method, addressed many challenges. However, during the early stages of the B-52 project, in-flight refueling posed difficulties. The early aerial tankers, powered by piston engines, had a maximum speed only slightly higher than the stalling speed of the jet bombers. In this image, the Y model grapples with the delicate task. The introduction of jet tanker refueling was clearly a safer and more preferable option. The advent of the KC-135 Stratotanker marked a significant turning point, making aerial refueling relatively safe and practical. Another approach to extend range involved incorporating extra-large outboard wing tanks, such as this example capable of holding 3,000 gallons, which could be jettisoned in combat situations. By March 1954, B-52s were rolling off Boeing's production line in Seattle. The planes then went into an induction program, where aircrew and aircraft were blended into one fighting machine. Inside this streamlined form, crews of 6 men mastered the intricacies of the Stratofortress. Compared to the B-36, Boeing's bomber was notably more confined, with every available inch allocated to fuel, payload, and electronics. While the B-36 boasted 6 gun positions, the B-52 had just 1. Instead of relying on multiple gun positions, the B-52 focused on performance and the emerging science of radar jamming for self-defense.
B-52 is a great plane because I liked flying it. It was a fun plane to fly. One of the most challenging things about it was refueling it. You get a plane that big, 500,000 pounds behind a tanker that's 350,000 pounds, and you got to transfer 120,000 pounds of fuel. That's part of the things that make it a great plane. It can go and go and go. I never got to fly it, but they used to fly 24-hour missions in B-52s, just refuel. So I think what makes a great plane where all the crews that flew it over so many years, my father was too old to fly it. I'm one of the younger people flying it myself, but there are probably 25 years older than flying it that are planes 10 years older than there.
The Strategic Air Command demanded the world's premier bomber, setting high standards for both its cutting-edge B-52 aircraft and their crews. Crew members underwent rigorous training, evolving into an elite corps of professionals, a team as adept as the sophisticated aircraft they operated. For over a decade, the Stratofortress and its crew held a singular responsibility, carrying and delivering thermonuclear hydrogen bombs. However, to serve as an effective deterrent, the bomb needed testing to validate its capabilities. Throughout the 1950s, hydrogen bombs were detonated in remote Pacific regions as part of these crucial tests. In the final tests, akin to many conducted earlier, B-52s were utilized to realize the formidable payloads. For the individuals involved, loading the most devastating device at that time conceived by human mind was a matter of precision and routine, a specialized task for the highly trained members of the Strategic Air Command team. Each cargo possessed a 100 megaton yield, a magnitude 100 times greater than the bombs dropped on Japan during World War II. In contrast to the weapons of that era, the device housed in this bomb bay would be decelerated in its descent from the B-52 by a parachute, affording the bomber more time to evacuate the area before the cataclysmic explosion. Driven by the concern of a potential Soviet atomic attack, the United States established an intricate network of detection facilities during the Cold War. Primarily located in the frozen north, the most probable route for a first strike, these early warning systems employed radar watchers constantly monitoring scanners scanning the sky for any blip. The Strategic Air Command maintained fleets of B-52s on operational standby, in a perpetual state of alert, poised to serve as the ultimate deterrent if the need arose. When the red phone rang, the procedure was automatic. Up to 100 Stratofortresses could be dispatched in a few short minutes. The routine was finely honed through regular exercises. The notion of an immediate retaliatory strike by the Strategic Air Command stood as the nation's best defense during the Cold War years. Entrusted solely to carefully screened officers, the task of nuclear deterrence fell upon the shoulders of nuclear-armed B-52 pilots, all holding at least the rank of major. They bore the weighty responsibility of commanding aircraft capable of altering or even terminating life on Earth. However, just as jets replaced piston engines, the B-52 and its high-flying Soviet counterparts were surpassed by a more efficient and lethal technology born in Nazi Germany. By the early 1960s, ground-to-air missiles had reached a level of perfection by both the US and the Soviets, making massive nuclear bombardment by aircraft challenging to achieve. The focus shifted to another delivery method: intercontinental ballistic missiles, or ICBMs. Years of development led to the creation of missiles like Polaris and Minuteman, eliminating the necessity for manned flights over enemy airspace to wage full-scale nuclear war. Despite this shift, SAC's Stratofortresses remained in service, as they still played a significant role in the precarious game of nuclear brinkmanship. The challenge with the ICBMs lay in their irreversible launch, denying politicians the time-honored tactic of saber-rattling and intensifying the risk of international conflict. The B-52, in conjunction with Hound Dog standoff bombs, presented a versatile alternative. Positioned at the very edge of enemy airspace, B-52s signaled America's preparedness to attack while allowing room for last-minute negotiations. The B-52's effectiveness was enhanced by the introduction of the quail decoy, which confounded enemy radar by replacing a Stratofortress's radio signal. Advancements after the Hound Dog led to the creation of the SRAM missile. Compact and deployable in greater numbers, the SRAM could be guided from within the B-52 to targets up to 100 miles away with remarkable precision. In 1965, the B-52 was employed for the first time in Vietnam. While now carrying conventional bombs instead of nuclear warheads, it retained its lethal nature. The wing mounts were equipped with 24 500-pound iron bombs, showcasing the adaptability of the aircraft in various mission profiles. The internal bomb load brought the total payload of each plane up to a total bomb load of 108. Throughout the Stratofortress's engagement in Southeast Asia, B-52s dropped over 3 million tons of bombs. While the use of these high-flying bombers stirred controversy at the time, there's little doubt about the Stratofortress's effectiveness in conventional bombing. Many historians contend that the extensive bombing of North Vietnam during the linebacker operations played a crucial role in compelling the enemy to return to the negotiating table, eventually leading to a ceasefire. In other Vietnam operations, more advanced bombs were employed. Some could be remotely detonated by personnel in other aircraft using infrared viewing equipment, synchronized with enemy activity. Standard 500 and 750-pound iron bombs were the norm for most B-52 raids. To expedite loading and turnaround, the internal bomb load was organized in pre-arranged racks, enabling swift installation. Crews stationed at Guam prepared for the lengthy 8-hour flight to the remote target. The crew in the front office and the solitary rear gunner assumed their positions as each aircraft readied for takeoff.
Well, the primary role of the B-52 in the Vietnam was basically tactical bombing of enemy troop concentrations. But it really started out, we used to cut roads early in '67. We did a lot of missions where we were interdicting trucks and supplies, but primarily we were cutting roads to back them up so the tactical forces could make the strikes. Later around Quezon, Son, we were really breaking up enemy troop formations. And we got very, very successful as they had to concentrate their forces. We became more successful at what the role of the B-52 could really bring to bear, which is massive air power.
Our defense posture provides the umbrella under which all competition flourishes in this capitalistic society. So the B-52, because of its tremendous design, lasted a great long time. And because of the philosophy and sometimes the tendency to forget history, which we seem to do in this country, it's lasted a long time as well. It's had to.
During the protracted years of the Vietnam War, nose art adorned more than a few B-52s, reflecting the personalization and character that the crews added to the aircraft. Although nose arts were milder compared to its Second World War counterpart, the missions undertaken were no less perilous. B-52 crews faced the challenges of swift and nimble enemy MiGs, anti-aircraft guns, and, most menacing of all, deadly surface-to-air missiles. Despite these hazards, they pressed on with their mission, embodying the resilience of soldiers who carry out their duties irrespective of opposition. Post-raid, ground crews hastily repaired the bullet-riddled airframes of returning Stratofortresses, preparing them for the next mission. Sometimes, the hits were uncomfortably close. Despite the low fuel takeoff policy, the substantial weight of the bomb load placed considerable stress on the engines, necessitating regular maintenance and often replacements. To ward off MiGs, rear gunners played a crucial role, occasionally shooting down the agile adversaries. These gunners operated from their solitary outposts, utilizing a radar-aimed, remote-controlled array of 4 cannons with devastating firepower. The tail gunner's position was omitted with the introduction of the B-52G and H models. All B-52G and H models were equipped with EVS, electronic visual systems, representing a technological advancement enhancing their capabilities. This enables the pilot and other crew members to see what is ahead of the aircraft, even in darkness and fog, via infrared television cameras and a monitor. This development came just in time as the role of the B-52 had changed from that of a low-level tactical bomber. Today's Stratofortresses may find themselves flying through atomic clouds, with the B-52 shielded by radiation-proof curtains and the electronic visual systems becoming the crew's sole visual connection to the outside world. Despite the evolving mission, red phones and flashing lights remain the standard currency of the Strategic Air Command. When the bell rings, whether in exercises or during wartime, SAC's formidable deterrent force leaps into action. The first order of business for the operations general is to abandon the ground base for the safety and mobility of an aerial combat post. Simultaneously, as the alert is issued, aircrews swiftly converge on their aircraft, perpetually on standby for immediate action. The general takes to the air, with the B-52s following closely. It is only in the safety of the skies that SAC's deterrent force can endure an attack while simultaneously being en route to deliver a response. A high-speed takeoff is deemed essential for survival. In these exercises, preparations are made for the possibility of a nuclear flash, and radiation-resistant curtains are deployed. At this stage, the crew becomes entirely dependent on the EVS and other electronic aids, as looking outside the cockpit becomes too hazardous in the face of potential radiation exposure. Flying low over the ground, each pilot awaits his orders. During this exercise, the B-52s are recalled, yet everyone involved acknowledges their capability to enter enemy territory if the need arises. The exercise concludes, leaving the general satisfied. After nearly 40 years of dedicated service, the B-52 continues to fulfill its mission effectively. But it is evident that the aircraft is approaching the conclusion of its service life.
We went over their arc light, which was 6 months at a time. And I did it 5 or 6 times, I don't remember. But the thing was, is you live with these people, you live with them, you sleep with them, you eat with them. They become brothers, so you trust them with your lives. You literally did, because if an EWO said brake right or brake left, you didn't ask why, you just did it. That means turn a plane left or right because there was a threat coming. You just did it. You knew that whatever he was telling you, he was in the plane with you. And vice versa. You never second-guessed the other guy because they were the expert in their position. And that's what the teamwork was. You learned to respect the other guy's position and how well they served the position. The B-52 is getting old. It does need a follow-on bomber, and I think the B-1 is probably that type of an aircraft. Next question evolves is, do we need the B-2s? I don't know. It's awful expensive aircraft.
Almost immediately after the initial B-52 rolled off the assembly line, the Strategic Air Command began the quest for a suitable replacement. The ill-fated XB-70 was an initial attempt, featuring an advanced design that became outdated due to the advancements in ground-to-air missile technology. More recently, there was a swing-wing B-1 bomber developed by Rockwell International. The B-1 offered a blend of high speed and altitude with its wings swept back, as well as more cost-effective low-level flying with the wings forward. The cost of deploying a large number of B-1s was deemed unacceptable to Cater administration, leading to the shelving of the project throughout the 1970s. However, in the 1980s, a revamped version, the B-1B, entered production. This time, not in the high-altitude role, but as a low-level bomber. Approximately 100 B-1Bs were deployed by the Strategic Air Command. Although the plane comes with a hefty price tag, if the B-1B proves to match the overall performance and value for money that its predecessor, the B-52, clearly demonstrated, it would be considered money well spent. After about 7 decades of service, spanning a period of remarkable technological advancements, the B-52 still stands as a weapon of formidable power and effectiveness. It remains a challenging act to follow in terms of its enduring impact and capabilities.
The F-102, 101, and 100 are all powered by the rugged J-57 engine developed by Pratt & Whitney. The individual engines vary somewhat, but for the most part are the same fundamental design. The J-57 is a dual compressor engine. The engine consists of the following components: the inlet, the low-pressure compressor, the high-pressure compressor, the diffuser case, combustion chamber, the first, second, and third stage turbines, the afterburner, and the exhaust nozzle. The low-pressure compressor, referred to as N1, is driven by the second and third stage turbines. The high-pressure compressor, N2, is driven by the first stage turbine. These two units, or spools, are not mechanically connected. The J-57 operates on the same basic principle as all jet engines. Pressure, presented in graph form below the basic engine outline, and velocity are increased by a series of rotors in the compressor section. A compressor bleed system prevents compressor instability when the engine is operating at reduced power. The compressed air passes through the diffuser into the combustion chamber, where the air expands, thus reducing somewhat the velocity and pressure. Fuel is mixed with a portion of the air to form the combustible mass. When combustion occurs, the gases are expelled through the turbine. At this point, power is extracted by the turbines to drive the compressors. The remaining energy, expelled through the exhaust nozzle, provides the thrust. Since exhaust nozzle and turbine discharge pressures are relative, turbine discharge pressure is used as a parameter to determine thrust. Thrust is the measure of force developed by the engine. Force is determined by mass times acceleration. Mass is the weight of air and fuel passing through the engine. Acceleration is the difference between inlet and turbine discharge velocities of this mass. Thus, thrust may be expressed by the formula force equals mass times acceleration. The engine trim charts are based on this formula. Additional thrust is obtained in the afterburner by increasing mass and acceleration at that stage. The basic engine pressure ratio during afterburner operation is maintained by increasing the exhaust nozzle area. Efficient engine operation depends on correct fuel schedule. The basic components of the J-57 main engine fuel system are fuel pump and fuel pump transfer valve, fuel control, and the pressurizing and dump valve. The fuel pump is a dual-element spur-gear pump. One element supplies fuel to the afterburner, the other to the main engine. The fuel control meters the fuel required to operate the engine through its full range. The pressurizing and dump valve supplies the main engine fuel manifold and drains the manifold at engine shutdown. At engine start, fuel enters the pump through the impeller where the pressure is increased. This provides the positive pressure head to the main stage. At this stage, the fuel reaches output pressure. The pressurized fuel closes the fuel regulating transfer valve and the afterburner check valve and flows into the fuel control. The main metering valve is closed at this time. A portion of this fuel passes through a minimum flow orifice through the signal line to the P&D valve. Since the control has been bypassed, pressure does not build up enough to close this valve until the power lever moves from cutoff to idle. When the power lever is moved to the idle position, the fuel dump valve closes. The main metering valve opens. The cutoff valve moves off its seat. The pressure loading valve opens. The P&D valve inlet check valve opens. And the fuel is supplied to the primary side of the fuel manifold through the pressurizing and dump valve. At approximately 74% RPM, the fuel pressurizing valve will open to supply fuel to the secondary side of the fuel manifold. The J-57 engine uses the primary and secondary system in order to obtain the highest possible fuel flow with the shortest possible flame. At low RPMs, only the primary side is used. When the emergency system is selected, the actuator positions the pilot valve to direct pressure to the shuttle valve system. The shuttle valve blocks off metered flow and provides support for unmetered fuel to the emergency throttle valve. This mechanical valve controls the flow of fuel. The afterburner element of the fuel pump will supply fuel to the engine in the event of main element failure. The primary function is to furnish fuel for the afterburner. The other components of the J57 afterburner system are the afterburner fuel control, exhaust nozzle control, igniter valve, and the mechanical shutoff valve. The relative position of the components varies according to engine model. The afterburner fuel control meters fuel to the AD spray box. The exhaust nozzle control directs compressor discharge air to open and close the nozzles. The igniter valve injects fuel into the combustion chamber, creating a streak of flame to ignite the afterburner. In the event of electrical failure, the mechanical shutoff valve will terminate AD operation at approximately 80% RPM. Rotation of this valve causes AD stage fuel to bypass through the AD fuel control regulator valve. The fuel control unit is carefully calibrated on the test bench to assure accurate engine fuel schedule. The main functions of the fuel control are to maintain acceleration schedules below compressor stall zone, to prevent over-temperature during acceleration, prevent lean die-off during deceleration, and to maintain any selected engine speed within operating limits, regardless of altitude. The fuel control senses engine RPM, inlet temperature, and burner pressure to supply the correct amount of fuel for any ambient condition. When calibration has been completed, all external adjustments, except the idle and military trim screws, are sealed. These seals are installed to protect test bench precision calibrations and must not be removed. The J57 engine will provide relatively trouble-free operation when all systems are functioning correctly. However, the systems must be properly rigged and adjusted. One of the most critical engine adjustments is the rigging of the fuel control linkage. Full range movement is obtained only when the fuel control and afterburner mechanical shutoff valve levers are correctly positioned. The levers are set to predetermined angles. A protractor or etched template is used to set the linkage at these angles. The protractor is positioned at the oil pump and accessory housing plug to establish a reference angle. This reference angle will be used to adjust the fuel control lever. With the fuel control lever in cutoff position, the difference between the reference angle and this reading must be the number of degrees specified in the tech manual. It may be necessary to readjust the fuel control lever to obtain the correct angle. The fuel control lever and serrated spacer are ratcheted to give the desired angle. The fuel control position, which, when all other linkage is connected, will close the afterburner mechanical shutoff valve. The power actuating rod is then attached to the fuel control lever. Move the mechanical shutoff lever to the detent position. The rod, connecting the cross shaft lever and mechanical shutoff valve lever, may have to be adjusted to the specified length. The AD mechanical shutoff valve is held in detent position, while the lever is ratcheted to the position where the rod, which has already been adjusted to the specified length, will fit. Then all connections are tightened. Either the protractor or an etched template is used to again check the angle of the fuel control lever. It may be necessary to readjust the fuel control lever to obtain the correct angle. After corrections are made, all connections are then safety. Replacement or adjustment of most components will affect engine operation. Prior to aircraft installation, the engine is thoroughly inspected and tested to ensure satisfactory performance. A fuel leak check is imperative before initial start of a repaired engine. With the system pressurized, check all fuel lines and connections. The exhaust nozzle opening must also be rechecked before initial engine start. Nozzle diameter not within specified limits will affect engine efficiency. On some engines, a fail-safe device is installed to prevent total loss of power in the event of linkage failure. The device will position the fuel control lever to a 45-degree angle setting, which will provide approximately 90% RPM, thus ensuring sufficient thrust to maintain flight. After installation in the aircraft, all airframe to engine connections must be checked and adjusted, and the engine retrimmed. Final trim, to compensate for aircraft installation losses, is preferably accomplished with the aircraft headed directly into the wind. Prevailing wind velocity and direction must be within limits specified in the tech manual. The trim pad area must be free of loose objects that could damage the engine if ingested. To effectively trim the engine, power control settings must be coordinated. Throttle linkage is operationally tested before making fuel control adjustments. Movement of the fuel control quadrant must synchronize with throttle movement. Power control movement is transferred to obtain predetermined fuel control settings. The aircraft manual indicates the relative degree of movement throughout the entire throttle range. Close attention to detail is required when trimming an engine. Changes in ambient barometric pressure and temperature will affect engine performance characteristics. True barometric pressure and correct temperature, both recorded within 15 minutes of the trim run, are used to determine target DC7. Target DC7 is obtained by tracing the temperature and pressure coordinates on the trim chart. Start engine is specified in the tech manual and allow engine and exhaust gas temperature to stabilize. Retard throttle to idle setting. Desired idle speed is obtained by adjusting the idle trim screw. As in all fuel control adjustments, final trim is always in the increased RPM direction. Proceeding with the trim operations, slowly advance throttle to military power. Allow 5 minutes for stabilizing. Caution, do not overspeed or overtemp engine during run-up and stabilization. With throttle set at military power, record RPM, EGC, and the turbine discharge pressure, EC7. If PT7 reading is low, return throttle to idle and readjust maximum RPM setting at the fuel control. Turn the adjustment clockwise to increase RPM in order to obtain target PT set. Advance throttle to military power. Stabilize, then recheck PT7. Return throttle to idle. Check EGC and RPM. Make certain that RPM is within 2% of data plate speed indication. At the completion of the trim run, follow standard shutdown procedure. Accurate troubleshooting depends on a thorough understanding of the J-57 engine and its system function. Only by correct analysis of the interrelated parameters can the malfunction be isolated. Proficient troubleshooting is the mark of quality. The Tech Manual outlines the common symptoms of engine malfunctions, the probable causes, and their remedies. Basic parameters used to determine engine performance must also be considered when analyzing problems. These basic parameters are RPM, PT7, and EGT. One of the most detrimental engine malfunctions is overtemping, or high EGT. Perform static checks of PT7 lines and connections, and the exhaust nozzle opening. Make sure the anti-icing valves are closed. Then check for instrument accuracy. All static checks have been performed and found satisfactory. Now the engine must be checked for proper drift. As engine approaches military power, check exhaust nozzle for creep. Check to make sure the PT7 has not exceeded target and RPM is within data plate limits. If high EGT still exists, the engine must be removed and the hot section inspection must be performed. Inspect the burner can for cracks or hot spots. Check fuel nozzles for loose, burned, or missing air caps, and evidence of seal leaks or clogged air holes. Check the first stage turbine nozzle guide vanes for excessive flow. Turbine vanes flowed beyond limit will distort the gas path, causing loss of turbine efficiency. The amount of fuel required to compensate for this loss accounts for the excess temperature. In conjunction with correction of the bowed nozzle guide vanes, or providing they were within limits, additional checks are necessary to assure the problem is correct. Inspect first and second stage outer air seals for cracks, burned areas, and damage to outer knife edges. Check clearance between outer air seals and turbine blade shrouds. Check first stage turbine dislocating dimension. The cause of high EGT may have been one major problem isolated at any phase of the investigation. or the accumulation of minor deficiencies requiring several procedures to isolate and correct. And RPM exceeded data plate limit during initial high EGT troubleshooting trim run, the engine would have to be seal cleaned before proceeding with other checks. This process is intended to restore compressor efficiency. When this operation is completed, retrimming the engine may bring all parameters within limits. When troubleshooting engine performance deficiencies, it is necessary to consider all three parameters: EGT, RPM, and PT7. As an example, failure to obtain target PT7 can be caused by many things. By comparing the relationship to EGT and RPM, many unnecessary troubleshooting steps can be eliminated. For instance, when all three parameters are low, a fuel scheduling deficiency is indicated. First, check for full travel of the power lever to fuel control quadrant. Military position must not be less than 54 degrees. The next step is to remove the fuel control and check the position of the camshaft. With camshaft cover removed, lever positioned at 11 degrees, and the temperature sense bulb in a 60-degree Fahrenheit bath, measure the distance from the end of camshaft to the cover flange. This reading should coincide with that on the camshaft depth plate. Tolerances and replacement instructions are included in the engine tech manual. The engine tech manual includes specific instructions for maintenance procedures. These manuals represent a vast accumulation of knowledge and experience. Through individual ability, initiative, and constant use of the tech manual, proper maintenance and troubleshooting procedures can be achieved. This is the goal of the Improved Maintenance Program.
Flying a 105 was the greatest experience a person can ever have. It was an airplane originally designed as a nuclear strike aircraft to be flown low level. It was extremely fast. In fact, it was the fastest airplane in the world till the F-111 came along below 10,000 feet. And it was a carrier-based ground attack airplane in Vietnam. And this airplane actually dropped more bombs in North Vietnam than any Navy carrier-based airplane.
You cannot place statues or build memorials in thin air. These airplanes, rescued, restored, returned to the sky, are the memorials. Through them, we give enduring thanks to those who gave everything they had to defend everything that we hold dear. By sharing them, we remind each other of the sacrifice. By sharing them, we introduce our heirs to their heritage. One week each summer, these national treasures are flown here. Twice each day, those who restored them present them to those who risked their lives to fight in them. And those who really did it tell the rest of us how it really was. It is a singular series of history lessons that anyone who cherishes liberty ought to see. As the Vietnam War escalated, Air Force and Navy pilots started flying more and more missions over Laos and North Vietnam. This was very high-risk duty. The North Vietnamese, thanks to Soviet support, had built one of the best air defense systems in the history of strategic aerial warfare. At this Warbirds in Review forum, two iconic aircraft of the Vietnam era, the Douglas A-4 Skyhawk and the A-1 Skyraider, and the pilots who flew them into those treacherous skies, were featured. Paul Wood, the founder and president of the Warbird Heritage Foundation, introduced the two aircraft. They are part of the Foundation's flying collection.
Our mission is to acquire, restore, and operate historic military aircraft. Two of our collection, we have about 12 in the collection right now, and two of them are here with us today. This represents our Vietnam segment of our museum. So we do have a website if you're interested in more information on either of these airplanes or any other airplanes in our collection. It's www.warbirdheritagefoundation.org. And we have lots of pictures and videos on each of the airplanes. We have cockpit pictures, we have maintenance pictures, so we have the airplanes taken apart. You can see inside, see what makes these things run. So you're welcome to get on the website, sign the guest book, and we send out periodic newsletters and things like that. So that's the pitch. So we have with us two phenomenal Vietnam era airplanes here. One is the AD Skyraider and the A-4 Skyhawk. Both played very, very significant roles in Vietnam. And the one to my right here is an A-1 Skyraider. And it was designed by a guy by the name of Ed Heinemann from the Douglas Aircraft Company, who was a very famous designer. And coincidentally, he also was the lead designer on the A-4 Skyhawk as well. Now, the next one over here real quickly is our A-4 Skyhawk. And it was a carrier-based ground attack airplane in Vietnam. And this airplane actually dropped more bombs in North Vietnam than any Navy carrier-based airplane. It was again designed by Ed Heinemann, the Douglas Aircraft Company, and it had nicknames of the Scooter, Heinemann's Hot Rod, the Bantam Bomber, and there's a great loyal fan base of the pilots who flew this airplane. Every time we have someone come up to us and say, I used to fly the Scooter, that's the best airplane I ever flew. And I tend to agree with them because I fly these things as well. So the Skyhawk was first produced in 1956. There were multiple models of the airplane. This is the same airplane, by the way, for those of you who don't know, that Jester and Viper flew in Top Gun as the aggressor pilots, so got a little notoriety there. They flew them they produced them until 1979. And the Blue Angels flew the F version of this from 73 to 86. About 3,000 of them were built. So a couple of significant points about this. When Ed Heinemann designed this airplane, the concept of it was to make it as light as possible so it could carry bombs, rockets, and fuel. So they left a lot of things out. For instance, this airplane doesn't have a battery. And most airplanes will have batteries or you can start them. But in order to save weight, they took the battery out. They took a lot of the oil scavenge and recovery systems out. So when they would ferry these airplanes from the West Coast to the Philippines, they'd do about 5 in-flight refuelings to get them over there. And the biggest problem was running out of oil, not running out of gas, because the oil system here doesn't recover itself. It just there's vents in the back, and so the oil kind of gradually leaks out over time. So the biggest issue was running out of oil instead of running out of gas. This airplane is painted up as an A4 Charlie model that was flown by a guy by the name of Lieutenant Commander T.R. Schwartz aboard the Bonhomme Richard in the Yankee Station. And Schwartz is credited actually with the only air-to-air kill by an A4 Skyhawk in Vietnam. He was on a ground attack mission and rolled off his target and found a MiG and shot it with some unguided air-to-ground missiles, and actually was lucky enough to hit the target.
The second airplane featured, the A-1 Sky Raider, was designed near the end of World War II. It became one of the Navy's workhorses during the Korean War.
The Sky Raider was first produced in 1946, and it was used in the Korean War initially by the Navy and the Marine Corps as a ground attack, carrier-based ground attack airplane, and it was quite effective, sort of taking the role of what a typical new A-10 would do at the time. The production run ran until about 1957, and over 3,200 of them were built. The engine is a Wright 3350. It's got 18 cylinders, 2 rows of 9, so there's 36 spark plugs in this thing when you have to change the spark plugs, so it's a lot of work. And it generates 2,700 horsepower, so it's one of the largest piston-driven airplanes that the Department of Defense ever had. Actually, I think it's the largest single-engine piston-driven airplane that they had. The airplane is about 11,000 pounds empty weight. But the significant part about this airplane is it can carry its own weight in fuel and armaments. So its max takeoff weight is about 22,000 pounds. So when you think about that, 11,000 pounds is what, 5.5 tons? And you can see some of the armament and bombs and fuel and things like that. And so it was really able to put a lot of armaments on target. And with its fuel capacity, it had the ability to loiter for up to 5 or 6 hours at a time. So it had great range, great loiter time, and could put a lot of metal on target. So it's about a 290 knot airplane, give or take. So it's not real fast, but it's built very, very strong and tough, and it could take a big beating. After Korea, the Air Force purchased about 580 of these from the Navy and converted them to A-1Hs and Js. They were used in the Vietnam conflict, primarily for special operations, search and rescue, and light ground attack. And there were several squadrons of these that were helicopter escorts to help provide cover for helicopters coming in and recovering down pilots. And so our airplane here is painted up like an A-1H from the 6th Special Operations Squadron, which was in Pleiku, Vietnam.
Dick Diller, an Air Force pilot learning to fly the massive Sky Raider, had a huge transition to make. In one way, airplanes fall into one of two design categories, either nose wheel or tail wheel. The Sky Raider is a tail wheel aircraft. All of Diller's previous training had been in nose wheel airplanes.
Yeah, that was a real transition. Out of pilot training, I got an F-106 assignment, and I flew F-106s for 19 months in the fighter squadron at Dover Air Force Base in Delaware in the 95th. And then I got assigned to the A-1, and when I got down to Hurlburt, we got, as Sam said, we got a tail wheel, we got a big reciprocating engine with cowl flaps and mixture, fuel mixture, and all the other things that are involved in an airplane with reciprocating engine. And so it was a real transition to go to a tail wheel, and the mission was different also. The interceptor was what we did in the F-106, going after incoming invaders, if you will, Soviet bombers. If they were going to come in, that was the defense against those. Whereas this mission was air to ground, and it was a totally different mission.
On December 5th, 1969, Dick Diller took part in what is still considered the largest wartime search and rescue mission ever mounted. Captain Benjamin Danielson and his weapons system officer, First Lieutenant Woody Bergeron, were shot down in their McDonnell Douglas F-4C Phantom, call sign Boxer 22, over the Ho Chi Minh Trail in northeastern Laos. It would be decades before Captain Danielson could be confirmed as having been killed in action. However, Lieutenant Bergeron was rescued after spending 50 hours in enemy territory. Search and rescue Sky Raiders were nicknamed Sandys. Dick Diller flew as a Sandy forward air controller for the Boxer 22 mission.
The Sandys went out, the Sandys were on 5-minute alert, just like we did in F-106s. And the alert schedule was the same type thing. So the Sandys rushed out to the airplane and launched and took off and went over about 60 miles east of the base is where the action was. And the first thing you got to do is you got to eliminate the threat of guns, because when you have guns that are firing at you, you can't bring a helicopter in to hover over a survivor and pick him up with guns shooting at him. So you got to get rid of the guns first. And so with the help of the forward air controllers, the Sandys, actually the Sandy low lead is the on-scene commander, and he comes in and he trolls low level trying to get the guns to shoot at him so they can find out where the guns are and try to knock them out. Now the problem with it was they put the guns in the caves and the karst. The karst were limestone formations that came straight up out of the ground, and they'd have caves at the base of them, and that's where they put the guns, so you had to hit them pinpoint. And that was, as I understand, I was told that was the very first time that the laser-guided weapons had been used to knock out the opposition. So then you can bring the helicopter up the river. The survivors are on opposite sides of a river, and you bring the helicopter up the river at low altitude and hover above them and pick them up. Well, the problem with it was the tail rotor on the helicopter that was hovering above the survivor got caught in trees. The aircraft commander on the helicopter thought that he was getting ground fire, and because of that he decided that he had to pull out, and as he pulled away, the survivor said, "Why did he leave?" He said, "I was 5 feet from the hoist. Why did he leave? I was 5 feet from him." And it just broke our heart because it was so close to getting the guy out of there, and we couldn't get him out. So we had to leave him overnight, and the next day it was more of the same. The problem with it was the first thing we heard in the morning from the survivor was that the front seater had been killed in the night. They didn't take prisoners in Laos at the time that I was flying over there. They just shot whoever they came across. And he said that after he got picked up, he said that what happened was the worst time was just towards dark when everybody had gone home. All the Sky Raiders had left and all the attack airplanes had gone. The worst time was just, it wasn't quite dark yet. They didn't have flashlights, but they still had a light illumination in the sky. And they came down to the river and they started looking for him. They found his place where he had been holed up there, and And he said that they shot their AK-47 into that area there. He said he had moved up the river about 50 yards, and he said if they turned around, they would have seen me. They left, and he survived the night. It was on the third day we finally got him picked up, and that was a cause for great celebration on the base. There was hundreds and hundreds of missions that had been flown in support of rescuing this one guy, and he's still alive and lives in South Georgia. His name is Woody Bergeron. He was originally from New Orleans. This passage was written in response to the mother of one of the guys that I had just flown with was shot down. And he was, I had just talked to him and became friends with him, and I had flown with him the night before. And the night he was shot down, I was going to go out about 2 hours later. So I was in briefing when the word came into the command post that he had been shot down. By the way, in my squadron, the time we were there, out of 20 pilots in the squadron, we lost 7 of our pilots. So it was not a good situation. But he was shot down, and he was in the same airplane I had been in the night before. Well, his mother didn't want to accept just that he wasn't going to come home, so she wrote a letter to the wing commander asking about information about what happened to her son, and this is why this passage was written in response to that. I was talking about, the letter made me realize why my mother was trying so hard not to cry that morning nearly a year ago at O'Hare International Airport when she and Dad and Emily saw me off. She had said, "Be careful, Dick." "I will, Mom, don't worry." I knew I was well trained, and I could only imagine the hazards that lay ahead. But now I knew about those hazards firsthand, and thanks to Rick's mother's letter, I could see a family side. The ones left at home a little more clearly, and that may have been the more difficult to handle. I have had it said to me, I don't know if I would have had the courage to do what you did, to face danger without flinching. You're lucky because you know you've got what it takes. Well, I never know how to reply to that because I don't know if I could do it again. All I know is I did it then, and I was one of the lucky ones who survived. That feeling of invincibility is essential to anyone who looks danger in the eye and keeps going. But the tragedies of Rick Shorlands and J.B. East and Clint Ward and Bob Moore and Dick Lytle and Jim Herrick and all my other friends who had been killed and the sadness of their families brought me back to the reality that we were playing for keeps and no one is invincible. What she had said in her letter, she said, I want to have more information about what he was doing, who he was flying with, where he was, and what happened to him. And then she wrapped it up by saying, a piece of paper is not much of an exchange for a son.
The F-105 Thunderchief, nicknamed Thud, was the largest single-engine fighter ever flown by the Air Force. It was designed in the early 1950s to deliver a nuclear bomb. Well, when that nuke mission seemed off the table, the airplane was reconfigured into a single-engine fighter and conventional weapons bomber. It did a great job in the skies over Southeast Asia. It had a short wingspan, only 35 feet. That's about the same as a Piper Cub, and it was 60 feet long and could reach Mach 2. That was only 10 feet shorter than a B-17. Dave Waldrop flew the Thud over North Vietnam.
Flying a 105 was the greatest experience a person can ever have. It was an airplane originally designed as a nuclear strike aircraft to be flown low level, single pilot, radar terrain avoidance, all weather. The airplane was extremely sophisticated. It was extremely fast. In fact, it was the fastest airplane in the world till the F-111 came along, below 10,000 feet. And it was an airplane in spite of its size, and this is what most people just can't comprehend. You probably, especially you that are pilots, you probably heard people talking about you wear the airplane, you become part of it and stuff like that. You generally wouldn't think of a big airplane that's some 60 feet long, 35 feet wide, that grosses about 53,000 pounds on takeoff, You wouldn't think of wearing that airplane. You'd think more of just flying the airplane. But once you got comfortable with the airplane, I did not even have to look inside at the instruments. I knew exactly where I was with that airplane. And it was because the airplane was so well balanced. And it was a terrific airplane in formation. And it would carry a lot of armament, and it would take a lot of abuse. And unfortunately, those poor airplanes, they got some abuse. It was just so solid, and like I said, it would take all this abuse and still get you home. And I've got pictures at home showing holes as big around as I am through the wing. One guy got hit with a ATOL, which is our version, or the North Vietnamese Soviet version of the Sidewinder. The thing actually went off, blew the back end of the engine, the tail feathers, turkey feathers, and for the afterburner and so forth, just blew them off. And the rocket motor actually embedded in the side of the airplane. He flew the thing home.
In the Vietnam era, aerial dogfighting, like in World War II, was largely a thing of the past. However, dogfighting did happen in Southeast Asia. U.S. pilots also had to avoid barrages of supersonic surface-to-air missiles, SAMs, which were deployed all around the Hanoi area. Dave Waldrop was transferred to Korat, Thailand, where he continued flying these high-risk missions over Hanoi. He explained why August 23, 1967 is a day he will never forget.
I got there, since I was already had more missions than anybody at Korat over Hanoi. They made me an immediate flight lead, so I was flying number 3 in crossbow flight. And we were going up on a big railroad yard, Yen Vinh Railroad Yard, which is just across the, not the Mekong, but the Red River from Hanoi. And it was such a big target that they actually were attaching 2 F-4 Phantom strike flights along with our 4 F-105 strike flights.
As Waldrop and his flight headed toward Hanoi, they were joined by Colonel Robin Olds and his flight of F-4 Phantoms. The Phantoms were there to deter MiG fighters who came up to attack the F-105s. Well, because the Thud was faster than the Phantom, the operations had to be very carefully timed to prevent the Thuds from outrunning their escorts. As the F-105s started their runs from northwest of Hanoi, the Air Force's radar surveillance aircraft, nicknamed Big Eye, was orbiting off the coast of North Vietnam.
And sure enough, Big Eye, and we hadn't seen very few MiGs during my tour. I started in May all the way through. I had probably, at this point, right at close to 55, 60 missions. Very few MiGs. And so they started calling bandits, bullseye. Bandits are what they referred to as the MiG. That meant that they're taking off out of the Hanoi area. Then they started calling out vectoring west. And well, this was an afternoon sortie. Where's the sun in the afternoon? Yeah, about 3 o'clock position, or I mean about 9 o'clock if you're looking at 12 o'clock, using that as a reference. So they was in the west. And these MiGs were taking off out of Hanoi, heading west, and we were coming in. Remember I mentioned the 2 refueling routes, depending on which way you were coming in. We were coming in from the west, overland, where we did our refueling. And so we're coming in, the MiGs are obviously up, they're headed out our direction, somewhere. So Robin says, okay, we're searching, we're looking for them. And we now have turned the corner and are heading toward Hanoi. We've gone around the backside of Thud Ridge, we're now pointed toward Hanoi. And we're just about to reach the push-up point. And the Big Eye starts calling, bandits, at your 6. And so everybody's looking. Force commander calls Robin and says, Robin, find these guys, get them off our ass. And so Robin said, I'm doing everything I can, guys. We're looking for them. And Robin Olds, and when he said he was doing everything he can, I promise you, he was doing everything he could. Well, Robin's doing everything he could, but he was trying to stay near us as well, so he couldn't go 40 miles behind us so he can throw his search radars toward us. That just doesn't work like that. And so anyway, two MiG-21s come through. They launch out two of their ATOL missiles, which I remember I said earlier is a heater, a heat seeker, and knock down two F-4s right behind my flight. So we hadn't even hit the push-up point. Now we got guys hollering, Mayday, Mayday, bail out, bail out. Beepers going off, and when you eject from one of these fighters, you got a beeper that goes off, and it sounds like, ew, 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 ew. We got three of those things going off because one of the guys did not get out of the airplane. We got three of those beepers going off. We're trying to concentrate on going inbound on the target. And guys, that was a lot of stuff taking place. And like I said, we hadn't even hit the push-up point. Well, but what you do, as I mentioned earlier, there's nothing you can do about those guys. There is no rest gap where they were. We kept driving. We kept driving right on in toward the target. And we did, and when we got to the target, I started seeing all these MiG-17s. Well, our job was to bomb a railroad yard, not to chase MiGs. So we're doing our thing now, and as a flight, we're all oriented in our positions for rolling in on the target. We're about 15,000 feet, and would roll in on the target, usually make about a 45, 90-degree turn rolling in as you approach the target. Right before I reached the roll-in point, the F-105 had probably the most sophisticated advanced fire control system of any fighter in the world at that point in time and space. It was deadly accurate. I've shot many air-to-air targets with that airplane. If you're smooth at all and you put the pipper on some part of an airplane, that's what you're going to hit. Well, the only thing you got to have the pipper. The pipper is a little dot. And then outside from the dot, you got these rings. There's two concentric rings, and it gives you a reference of how big that airplane is, because you can see as you're getting closer, obviously his wings are going to fill up more of that area. So you had an idea of your range, how far out you are. Plus, when you had your radar working and locked on, it's telling you exactly how far out it is. It was beautiful. Well, the only problem is you got to have those rings and a pipper up there to use them. And my bulb burned out as I was approaching the target. That means I'm looking at just a clean windscreen, and it's just like there's just glass up there. And so I had no sight, but I said, well, I've been here, done this many times, so I just rolled in. I looked about right, and at 7,000 feet, I pickled off. I pulled hard to the right like our flight leader had briefed, and I started looking for him, and as I'm looking for him, I look up, and heading west away from the target area was a F-105 Thunderchief. He was going straight and level, which is absolutely, like I mentioned earlier, an absolute no-no. And there were two MiG-17s right on his butt. The lead MiG, it's got a 37 millimeter, I think it's 37, 35 millimeter cannon in the nose, and that thing is going poof, 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 just like that. I could still see it like August 23rd, 1967, the picture I was looking at. He's shooting at this 105. He's only about 1,500 feet behind him. The guy's going straight and level, had no clue these MiGs were there. And I holler out over the radio. I said, 105, head west, you got two MiGs on your ass, do something. Of course, there was 20 105s up there. And he just kept driving straight. And in all fairness, what we generally did is switch over to our flight frequency, because there's so much chatter up there, so much conversation, you couldn't communicate as a flight to get rejoined. And so he probably never heard it, but still he was going straight and level. So I said, well, here's your shot. And I said, I got to get these guys off of him. I had a Sidewinder. Remember, that's a heater. And it seeks out the temperature. It looks for the heat signature from the jet engine. And that's what it hones in on. And my Sidewinder, and it makes this growling sound in your headset when it's got a heat source. And it was looking at that damn heat source, and it was just screaming its head off. Come on, Dave, let me fly, let me fly. And I look at that 105, I looked at MiG behind him. I couldn't do it. The 105's engine is probably 4, maybe 5 times bigger than a MiG's engine, putting out that much more heat, and I could never have lived with myself if I let that thing fly and have it go to the 105. Remember, I didn't have a sight. That would have been the way to go. So anyway, I just turned the volume off on the Sidewinder, and I punched everything off the airplane. My tanks, my bomb rack. That was back then that was a Cadillac, $6,000 for a bomb rack. I punched it off with a panic button, and I still left my outboard pylons. In other words, I had my Sidewinder still, but I lit the full afterburner. I half-G'd the airplane. Anybody that flies airplanes know that when you unload a wing on an airplane, you remove the induced drag off that wing, and you really can start moving. Well, the 105, it was in its element now, because that's what it did. It went fast. So I lit the torch. I dove down so I could come up underneath these guys. So I'm sitting there trying to figure my game plan. Now you got to remember, I'm just a dumb shit lieutenant. And so I hadn't got as much experience as a lot of these fighter pilots have got. And I really do mean that. I wish I had of, because I could have probably thought through this thing a lot better and been more prepared for it. But I did do the best that I thought I could at the time. So I took it low so they wouldn't see me coming. And I decided, well, I'll roll in on number 2 and try to swing over on number 1. The last thing I saw on my airspeed indicator was 1.3 Mach. For those that don't, Mach 1 is supersonic. That means I'm doing right at about 900 miles an hour. Something like that, right? And I didn't realize at the time how slow this 105 and the MiGs were going. I really didn't. I know one thing, they didn't have their burner on, which the MiGs did not, and neither did he, which sort of surprised me, because you would think the MiGs would have to have the burner on to keep up with the 105, period. But you know, there was a lot going on, and that just hadn't quite sunk into my computer yet. And but they did not have the burner going, so I'm smoking now, and so I'm coming up low, and I'm starting to make my pull toward number 2 MiG. All of a sudden, now my eyeballs start getting a sense of speed differential here, and I realize that I am absolutely it's smoking like hell, and I'm gonna overshoot, and that's the last thing you want to ever do, is overshoot and have an enemy airplane positioned behind you. So what I did is I pulled hard. In fact, my G meter when I got home was 7.5 to 8 Gs. I did it smooth though, so that made it okay. And I pull and I open up with my cannon. Now the 105 had one of the finest air-to-air weapons in the world, which was a 20 millimeter cannon. It's a Vulcan cannon. It had 6 barrels. It fired 6,000 rounds a minute of 20 millimeter, and we had high explosive shells on board. And so I start my pull, and I just, well, I'm opening up on, and I was actually on his left side, and I thought I saw a flash on his left wing that where I hit him, but like I said, I was just smoking, and so I didn't get a chance to really dwell on it very long. And so I'm going up now. I'm almost vertical. There was a broken layer of clouds, and with the clouds, it was sort of like, well, just assume where his knees are, there's a cloud layer. And they were broken. And when I went up, I just went up screaming. I popped my boards. I go up over the overcast, and I'm sitting up there, upside down, inverted, saying, "You stupid lieutenant, you had one shot at a MiG and you blew it." At about that time, remember the cloud layer's right about here. Out from underneath this cloud layer is a MiG-17 with his afterburner going. I'm sorry about that, guys. And I said, oh my God. And so I'm sitting up there inverted. The MiG's right here. I pulled my nose down, I just eased forward a little bit on him, open up, and the first shells went right through the cockpit. Now that might sound like something that's okay, but there still was respect for the pilots in these other airplanes. I think you've seen plenty of World War II, cases of this. But anyway, the first bullets went right through the cockpit and worked their way down the left side of the airplane. And while I'm actually shooting at this guy, if you ever see my film, you'll see this. 105, totally, he never saw this because we talked about it when I got back, to Karat. He never saw us, but he went right between us. A big ball of fire comes out behind the 105. And I never saw, I didn't really realize what was going on until later. But apparently I had a drop round, because he was below my firing line. And apparently I had a drop round that caught his fuel tank. And at that, with all the MiGs, everybody punched their tanks off, so nobody brought home a compromised tank with a hole in it. When they got back to Kokoda or Karat, everybody had clean airplanes, so we never found out who that was.
During the question and answer period, Dave Waldrop described the techniques they used to neutralize the SAM threat.
Well, yeah, what you're talking about, some of our SAM evasive tactics, yeah, obviously we didn't just sit there. If a SAM's coming your direction, you don't just sit there and wait to see if it hits you. And I don't mean that to be smart or nothing. But you'd have to see it. You'd have to see it and project its trajectory. And what you would generally try to do from where we were located, our best defense was to brake hard into the missile and down, because it's got a certain amount of acceleration momentum. And like I said, that thing cranks up to about Mach 2 by the time it's getting to the target area. And so our best tactic, if we saw it, was to break into it as fast as we could go before it had a chance to change direction and home in on it.
Richard Nixon said, quote, "No event in American history is more misunderstood than the Vietnam War. It was misreported then, and it's misremembered now," end quote. Perhaps the best antidote for misunderstanding and misreporting is to simply listen to Dick Diller, Dave Waldrop, and the hundreds of thousands of others who served in Southeast Asia. On this day, their collective experiences, told in their own words, certainly had the Warbirds in Review audience thinking and remembering.
Aviation, the art of aeronautics, began with the dreamers, inventors, and daredevils who dared to defy gravity. The journey of aviation was nurtured by pioneers like the Wright brothers, whose first flight marked a historic milestone. The role of aircrafts in world wars was groundbreaking, dramatically changing warfare strategies. This initiated a technological evolution in aviation, transforming the simplistic wings of a biplane into the thunderous roar of jet engines. Let's journey through the ages of aviation. Behind every great aircraft, there were great minds. These visionaries, like Sir Frank Whittle, the innovator of the turbojet engine, redefined air travel. Then there's Skunkworks' Kelly Johnson, the genius behind the SR-71 Blackbird. His designs combined speed, stealth and power, crafting machines that dominated the heavens. The contributions of these pioneers have left an indelible mark on the canvas of aviation, shaping the course of history and inspiring generations of engineers and aviators. Each epoch in aviation history gave birth to extraordinary aircrafts, each with their own unique features and roles. The Lockheed SR-71 Blackbird was a marvel of speed and stealth. The F-105 Thunderchief, a supersonic fighter bomber, was vital in the Vietnam War. The P-51 Mustang, a long-range fighter, was critical in World War II. The P-47 Thunderbolt, a heavyweight fighter, was used extensively in the same war. The A-10 Thunderbolt II, the Warthog, is a close air support icon. The Messerschmitt Me-262 marked a leap forward in aviation technology. Each of these game changers were instrumental in their eras, and their legacies still resonate today. Beyond the game changers, there are those that have transcended their practical roles to become icons. The Concorde was not just an aircraft, it was a supersonic symbol of luxury and speed. The B-52 Stratofortress, a strategic bomber, is an icon of power and resilience. These magnificent machines and others like them have become much more than just aircrafts. They are enduring icons that encapsulate the audacious spirit, the relentless innovation, and the boundless ambition that define the world of aviation. For more amazing aerial footage, and to join us in this incredible journey, check out the Dronescapes YouTube channel.
If you enjoyed this video, please remember to like and subscribe. And as always, thank you for watching.